So I think from my side, for some reason, screen sharing is disabled.
Yes, sir. We have made you co-host.
Oh, okay, okay, okay. Is my screen visible and am I properly audible?
Yes, sir. Screen is visible and you are
Okay,
audible also, sir.
okay, okay. Thank you.
If possible, can you increase your voice little bit, if possible? Otherwise,
Uh, uh, Pardon? Uh,
if possible, can you increase your volume? I say.
okay, 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 okay. Yeah, is it fine now?
Yes, better.
Okay, okay. I'm just holding the mic closer to my mouth. That's it.
Okay.
Okay, okay. So this is my larger research interest. I would start with this. So if you consider news broadcast analytics system, you can also consider this as uh, one kind of an IoT system, because if you look at different kinds of sources of news, so what are the different kinds of sources of news that are there around us? So one is news broadcast that is available from television. So there are different broadcast agencies. They broadcast news and they edit the news, prepare the news, and then they broadcast the news to us. Then similarly, there are web news articles where people may either post certain news events through blogs. There may be opinions, there may be real news events, because there are personal channels as well. There are similar personal channels on social media. So that may be Twitter, that may be Facebook, or that may be news channels of certain media houses, or there may be news channels or announcement channels of certain agencies. Similarly, there are radio broadcasts that are available. So you see, there are different modalities of news that are available. So one is a visual modality, one is audio modality, pure audio modality, and then there is pure text modality. And then there are image modality, like with news, web news, there are often images that are available. So there is fixed image, static image, there is video in which we get a number of images, time indexed images. Then we have audio along with that. We have pure audio, we have pure text. So there are different kinds of information that are available. Along with that, there is auxiliary information to support historical data. For example, Wikipedia or Wikinews, news archives, they are our auxiliary information. Now, what we want to do with this is this. Suppose today you would like to have one analytics. By analytics, say suppose you want to know that historically which city is the safest city in India, or if you want to know that how many murders that happened in which city. Now all the news channels are already reporting that, or if you want to know in your city how many murders happened in these many places, or how many bomb blasts that happened. These are the negative events. Or if you want to know how many times what are the cricket scores and things like that, or whose opinion is what. Now these are the kinds of analytics that you want to know. But typically if you look at a TV feed or a radio feed, it is not searchable. Or in other words, this data is not structured data. So this data is not well organized data. So you need to process this data so that this data can be made structured and organized data. So for that we need a broadcast segmentation, and you need to extract the stories out of that. Now see, in a broadcast there are many other things. There are debates, interviews, opinion articles, all these things. So you may need to have an opinion analysis system, you may need to have a knowledge base. You can design a user interaction in which you can have an AI anchor who can do conversational AI for all these things. You can have a data visualization system, knowledge base. You should have event discovery for this. For example, all these news articles are publishing different kinds of events. So for that, you need to discover that which real world event correspond to multiple news stories. Because say NDTV will report the same event in one viewpoint, Times Now will report the same event with another viewpoint, but you need to relate that this is the same real world event for which these are the different stories. In a radio feed also you will see the same story and somebody will also write about that event in the Twitter. So you need to relate them and then index them. So you need to have a story ID, news story, video segment, linked web news articles, linked Twitter segments and all these things. And you have to index them with metadata so that when the visualization is required, you can call them. So this is the larger goal that we have as a research goal in our group. Now, as a first step towards it, we have simply gone for segmentation. Now here we just show that how TV, for example, has grown in our nation. So in 1982, around that time, Doordarshan was born. And in 1995, we had a 24/7 news channel, which was Star News. Then by 2000, we have 12 satellite news channels, and then there are 30 cable news channels. And now by 2016, we have 380 plus satellite and 800 plus cable news channels. Now it is extremely difficult to manually monitor such news channels and note down that how they are reporting. So definitely we need automated systems for that. So we had a project from the ministry for as a first step towards this work. In this we have done this. We have considered only web news articles and we have looked at TV news broadcast. And then we have segmented the broadcast and then we have looked at debates, interviews and news stories and then we have indexed this. Now today I'm not going to talk about that. I'm going to talk about a very small part about this in this work. So this is an overview that when we capture data from this TV feeds, so we have this TV news broadcast acquisition system from which we get digitized broadcast videos. The first step that we have is from these videos, we perform a video short segmentation. So what are these video shots? Now by short, we mean this, that suppose in a movie you are looking at say Amitabh Bachchan and Rajesh Khanna speaking to each other. Now the camera is on Rajesh Khanna and then there is a background associated with Rajesh Khanna. And then the camera again looks at Amitabh Bachchan and then there is a background associated with Amitabh Bachchan. So you see, if you look at the image properties when the camera was towards Rajesh Khanna, it had different kind of a feature distribution. And then it completely changes when the camera looks at Amitabh Bachchan because the color distribution changes, other feature distribution changes. So these two are two different shots. So in news, when news is presented, we also find out these different shots. When shots change, different kind of changes may happen. Say that TV news presentation style may change. It may switch from the anchor to some field shot, or it may switch from one anchor to another anchor. So we always look at these shot changes and we assume that each shot contains very different content, at least semantic content. So our very basic unit is a video shot and we try to work on all these shots. Now, if you look at our television today, then the entire thing is very much advertisement driven. Now, many systems, many of our present agencies are interested in monitoring advertisements as well. First of all, you will be very surprised to know that advertisements are also source of some kind of communication as well. Because say, for example, there is a one time only some advertisement came up. Is it to trigger a sleeper cell? Nobody knows. Some product nobody has heard of, but one advertisement came up and then gone. Okay, is somebody actually signaling something using that advertisement? Now, Pepsi wants to know that what are the programs that Coca-Cola is sponsoring, so that similar programs Pepsi may also sponsor. Also, say for example, Surf Excel has given some money to some program as a sponsor. Now they are interested in knowing, they also put some other agency and find out that whether they are really showing the entire Surf Excel advertisement properly or not. Also, there are constraints like this, that if in one slot you are showing Surf Excel, then no other detergent uh, advertisement will come in that slot. So basically, in between two non-commercial blocks, there is one slot for advertisement. Also, there are rules that are given by the Broadcasting Ministry that there should not be more than this much of advertisement in 1 hour of broadcast. However, these rules are not strictly followed, that we have found out. Now, these also people want to monitor and find out whether advertising rules are properly followed or not. Now, in our case, advertisement is something that we do not want to analyze. Although there are agencies, there can be a project in which you may need to target the advertisements only and then focus on the advertisements, because people have also contacted us asking for advertisements and finding out what all advertisements are being played. So here we are talking about advertisement detection and removal. After that, we are going for different channel contents like programs. In programs, we can find out debates, interviews, and news bulletins. And in news bulletins, we find out the stories, news stories. And these news stories are segmented and stored. That was our ulterior motive. So let us look at how news narration started. So effectively in 1936, if you look at the history, news narration was performed with pictures broadcasted twice a week. In 1950, 4 news networks were launched in USA. In 1954, John Cameron first TV-only news anchor, and it was a 15-minute show. And in 1960, there was a report first multi-host show with field correspondents. So please know this is the first time that field correspondents also came in. Then 1970, 6 to 8 bulletins of 30 minutes each per day. 1980, first 24/7 all news channel. And in 1982, we said that national television network launched in India. Then in 1995, 24/7 India's first news network channel. And then we have discussed earlier, by 2000 we had 12 satellite and 30 cable news channels, and by 2016 this is our latest report on this when we were doing the project. So there were more than 380 satellite and 800 plus cable news channels. So this is how news evolved, and slowly after around 1980 onwards, things became more dependent on advertisements. Now, this is how TV broadcast is produced. Initially, the field correspondents and others, they bring in the stories, that these are the stories of the day. And then programs are produced with interviews, debates, news bulletins, etc. And then advertisements are put in between so as to create the entire TV broadcast, which is then broadcast to the air. Now, this is a broadcast day that we generally see. So if you see the night of 2 to 6, so this time generally we do not see the TV, it is called the graveyard hour. Then 6 to 10 is the early morning, 10 to 7, 5 p.m. is daytime, where generally events happen, and any live event is typically shown here. Then 5 to 7 is the early fringe, and 7 to 11 is the prime time. Here we have the highest viewership. And these two graphs show how the average number of TV viewers has grown from the year 2015 to 2016, even when there was internet. Now, this is our pipeline for TV broadcast segmentation. We have the TV broadcast. First, we take out the advertisements and channel content, and then the news program level segmentation, where we take the news bulletins, debates, etc., and then the story level. But we will not go into that in this talk. We are only going to talk about the advertisement detection in this talk. So let us see how to do that. So here we start talking about television commercials. So this is just a list that we have obtained from the ministry, that what are the things that are not to be carried in the broadcasting service. So nothing should be shown which offend against good taste or decency, contains criticism of friendly countries, contains attacks on religions or communities, etc. So there is a long list of things, and it is really very hard to implement. Even when you detect advertisements, that is not all. One may go ahead with a much larger project of detecting whether the advertisements are violating things or not. That is why you may see that the broadcasting ministry gives you sometimes this notification that if you see something, it is basically crowdsourced. So if you see something which you find abusing, then please report to the ministry. Now, automated systems are now coming up which can automatically detect certain things that are that are violating these rules. Now, we have one agency known as Electronic Media Monitoring Corporation. So this Electronic Media Monitoring Corporation have more than 10,000 employees who are looking at these television feeds, and they are finding out. So this is from their report, that what are the kinds of violations that are there in television content. Now this is from large scale recording and monitoring. So total number of TV channels in India is 763. Now 670 plus advertisements per channel per day. So more than 5 lakh advertisements to monitor each day. Now you see EMMC detects on an average only 1400 out of expected 1 lakh violations each month. Then commercial monitoring plays a key role. So you need to find out who sponsors which show. Are some commercials conveying information, as I told you about the sleeper cell issue? Are they violating broadcast rules? So these are the things that we collected information from these places, that they are talking about the violations, the number of violations, and why commercial monitoring is very important. So these are just some examples which all of you are familiar with. So you can see that the commercials have some unique features which are not there in the non-commercials or the television shows. For example, in the commercials, you will may see that there is not much text. On the other hand, when you see the news reports, etc., or debates, etc., there is a lot of text around. So the presence of text can serve as your information. Also, commercials have to convey a lot of information within a very short time. So that is why the short length, video short length of each commercial is very small. That is also another feature that commercials have. Also, you may note that when TV commercials are played, the volume suddenly increases. That is because they want to draw your attention. And commercials have a lot of motion because they display a lot of motion to get your attention. So you see presence of motion, then the usage of color and contrast, then high volume. These things are typically, and placement of objects in the center or certain places. So these things are typically used in the commercials to get your attention, and those in turn can be used as features to detect commercials from the non-commercials or the TV channel content. So it is not that there are no commercial products available for advertisement detection. So there are certain things that are based on use of near copy detection. So these are known as the method of fingerprinting. So what it does is these are mostly applicable for cases where you know that which commercial is to be detected. Say for example, Pepsi said that their commercial is to be detected, and it is to be found out that in which slots the Pepsi commercial is floated. So since if you know the commercial of Pepsi, every commercial is to be hashed using their feature vectors, and then the Pepsi commercial will also be hashed, and using that using a very high speed technique, since they are all hashed, you can search for the commercial. So these are like use of near copy detection. Now, a generic advertisement detection is different from this. So a generic advertisement detection relies on machine learning algorithms and uses the audio video features, but it also suffers from different challenges. It also faces a lot of challenges. So the challenges are this, that see, it has to work on all channels. Now different channels has different kind of content properties. For example, if you look at Cartoon Network has a lot of motion, and it may match its content based on motion feature may match with that of commercials. A music channel has loud music, so in terms of volume or sound intensity, it may match with that feature. In terms of commercials, many commercials are only musical. So there are multiple challenges that are there. So not for all channels that this thing will work. For example, if you make a detector that detects very well for news channels, will go and completely fail for generic channels. Yes, is there a question? Okay. So here goes a problem, that how do you select features? Because different features work for different channels. Now then there is an imbalance in samples from positive and negative class. So the channel content, that is a large volume of data, whereas advertisements is a much lesser volume of data. So it is a well-known issue that if you have imbalance in data, then your classifiers do not perform very well. And then comes the generalization capabilities. So if I train on a certain number of channels, will it be able to perform on other channels? So that is the issue of generalization capabilities. So these are the three challenges that we faced, and we tried to propose a classifier for working with generic advertisement detection. So this is one statistics of the data set that we have created from different channels. So we looked at 5 different channels which are completely different in terms of their characteristics. Say for example, Star Plus, Cartoon Network, HBO, National Geographic, and Sony 6. So we are looking at these statistics like average number of shots that are there per hour. So you see in Cartoon Network, the total number of shots are very high. Even in Sony 6, the total number of shots are very high. Whereas HBO is a movie channel, there the total number of shots are pretty low. That means the shot changes are not that high. Now average advertisement duration per hour in terms of minutes is this. Whereas advertising code in Cable TV Networks Regulation Act prescribes a limit of 14 minutes per hour only. And apart from HBO and Sony 6, everybody else is almost violating that. So average number of advertisement shots per hour, that is also given here. So you can see that average number of advertisement shots as percentage of shots per hour is this. So this shows you that what is the imbalance in the data. Now with this data set, we have tried doing this, and we have recorded around 40 hours of data from each of these channels. So these are the list of features. I am not going into explanation of these features. These are the audio visual features that we have used. We have used these color features. To look at the structure of the image, we have used the gradient feature by looking at a distribution of the gradient of the data. We have used motion features to capture that what is the distribution of motion. We have looked at audio features. We have looked at distribution of faces, and we have looked at distribution of text in the image. So mainly these are the features that we have looked at. Now these are the generalization challenge. So generalization as a challenge we have already discussed. The challenge is this, that every channel is having its own policy of presentation and editing format. So since the presentation and editing formats are different, so it is only natural that capturing the negatives, that means the channel content, by using a same classifier is going to be a hard thing. So the channel content is having large variations. For example, Cartoon Network has synthetically generated graphic content, whereas National Geographic has mostly natural videos. Now Sony 6 has high speed and loud music because Sony 6 is having a lot of movements in these music videos and all. Whereas movie channels seldom use, like HBO for example, loud music in the content. So these are the variations that are there. So for that we have performed a performance an analysis of the performance of features. So what we have done is we have tried to detect advertisement and channel content using only one feature. So for example, only by using the group of color features. And we have seen that there is a difference in performance of the positive class and the negative class. So when we see that there is a difference in F score of performance, so F score is, by the way, the harmonic mean of precision and recall. So when we see that there is a difference in the F score of any of these positive and negative class, then that tells us that the classifier is biased with respect to this feature. So this will not perform well. So that was our observation, and we saw that none of these features alone can perform and detect this. By the way, the features are not our proposal. So what we have done is we have gone into the literature and we have seen that people have tried solving this problem, and some people have proposed certain of these feature combinations, some people have proposed certain other combinations of features. So we have merely taken all the features and we have grouped them, and then we have tried to see that how each feature group performs. So if we take all color together, color feature proposals together, how they perform. If we take all gradient features, if we take all motion features, then how do they perform? So we have seen that there are differences in performance. All the audio features turned out to be good in case of cartoon channel, entertainment channel, movie channel, science documentaries, etc. So it is sure that we have to do some kind of a feature selection, or we have to come up with one algorithm of a classifier which can work with the features while selecting the features properly.
Sir, I have one question here.
Yes.
Sir, you are saying advertisement as a positive and channel content as a negative. It should be reverse.
Actually, here we are. It is up to you when you are performing the problem detection problem. It is
Okay.
up to you which one you assign positive or which one you assign negative.
Okay.
So in
Means
our case, yeah,
it's
it
all
is up to you.
assumption. Okay, okay. Okay, sir.
So in our case, for example, advertisement is something that we are going to detect. So
Okay.
we consider it as positive.
Okay, sir.
Okay. So now we will go towards the classifier that we proposed. So before that, do you have any questions from the audience regarding the features and all? So in discussion on features, I have just shown that it is not sufficient to use any one group of features, because they are showing that we have shown that if we look at any one kind of channel, say entertainment channel or cartoon channel, we are showing that none of the features are performing properly. So because you see the highest performance is 0.7 or 0.55, etc. And along each feature, there is a difference in the positive and negative class, which shows clearly that there is a bias in the classifier because of the imbalance in the data and all. So any questions up to this?
Any question from participant side?
Yes, any questions from the participants?
The commercials would normally show a lot of emotions. So is it possible to look at the face and find out that? I mean,
Commercial should normally show a lot of
emotion. I mean,
right. So that's
somebody in a
why.
hurry, somebody is very happy, type of a thing.
So if you look at the features, one is color features. So there is also a face features. So we are not looking at emotion. Say for example, in a car advertisement, generally you may not see the face of the person, only possibly the car and all. Only a few shots may talk about the face, but we are looking at how many faces are there and where the faces are. So we are looking at the distribution of faces. So we are looking at how much of the screen area is covered by the face and where is it and how many faces are there. So these are the face features that we are using, but we are not specifically looking at the emotion.
What is this number 512 and 766? Does this mean?
Where?
Like the first one, like rank histogram is 512.
Oh, 512D is 512 dimensional.
I see.
So distinct color score is a single score. So it is a one-dimensional thing. Ranked histogram is a 512 dimensional. So if you put them together, you can see it is basically a vector which has 512 plus 1 plus 766 plus 256 into 3 plus 32 into 3 plus 1 plus 256, that many dimensions. So it is a high dimensional vector together. Okay.
Okay, thank you.
Yeah.
Sir,
Any other questions? Yeah.
Sir, what is the time it required? Means it is such a high computation. So means you must. What are the hardware which you required for this
Oh, okay.
calculator?
So I have not included the picture for that.
Okay.
So we have implemented this entire system using 12 computers and one workstation. Okay.
Okay.
So basically what happened is we have put three computers for each channel. So there were 3 TV channels that we monitored, and we had a latency of something like 47 minutes. So basically, while 1 hour of data was getting we have recorded in chunks of 1 hour. So for example, when data of 9 a.m. to 10 a.m. is getting recorded, then we are processing the entire video of 8 a.m. to 9 a.m. Okay. Now we had a pipeline. So in that pipeline, say for example, 3 computers are associated to the processing of this thing of 1 hour of data. So in this 1 hour of data, the first stage is this short segmentation. Now while downloading the recording itself, we were doing the short segmentation. Now you see these feature computations came in. Then these are level 1 feature computation. So this level 1 feature computation, much of these were done in parallel. Okay, in these 3 computers.
Yes, sir. So you use GPU kind of thing for this?
No GPU.
No GPU.
I mean, when we got this project, it was in 2013, and the
Okay.
ministry did not give us enough money for a GPU. So
Okay.
we have done everything on CPU. It was a quad-core CPU. So we have used 3 cores for each of these quad-core machines, and 3 machines were used in parallel to do this level 1 feature extraction. Now once that is done, because our first task was the commercial detection.
Okay, sir.
Okay.
Yes, sir. Thank you, sir. Thank you.
Yeah. Sure. Any other question?
I think this Navya Shri has raised the hand. Somebody called.
Okay, I cannot actually see this. So if someone has a question, please go ahead, because I can see my screen only.
Yes, Navya Shri, if you have any question, please ask. Sir, you please continue.
Okay. So we'll start with classification trees. So by classification trees, we will discuss this classification algorithms known as decision trees. So everybody is familiar with this puzzle where somebody asks you that you guess a number between 1 to 20, And if you guess a number between 1 to 20, then how many questions shall I ask you to get that number? So this is basically a binary search problem, and you will ask the questions like this, that whether the number is greater than 10 or less than 10. So if it is greater than 10, if your answer is yes, it is greater than 10, then you will ask whether it is greater than 15 or less than 15. And if it is greater than 15, then you will ask whether it is greater than 20, 18 or less than 18. So this way we will go ahead and come to the number. So if you look at the flow chart of this questionnaire, question sequence, then it looks like this: greater than equal to 10, yes or no. Then the search space gets divided into two parts. One is 10 to 20 and 1 to 9. So when you ask this 15, it gets further divided into 15 to 20 and 10 to 14, and there 1 to 4 and 5 to 9. So effectively, by asking each question, you are dividing the search space into two parts. And finally, this entire search space gets divided into this 1, 2, 3, 4, 5, 6, 7, 9. So maybe by asking some more questions, another question, you will get the answer. Now the beauty of this is you will be asking only a few questions to get the answer by avoiding a linear search. So that is the beauty of a binary search. Now, and this entire thing can be represented by a binary search tree. Now this specific thing was taken up by the machine learning community, and they thought that why not implement this in the form of a classifier, where we can decompose the entire feature space, where each feature is having its class level. Why not we can hierarchically say, for example, here if you go from X to the search space, we are actually hierarchically decomposing the search space into a top-down manner. So it is a hierarchical top-down decomposition of the search space. So in machine learning also, people thought that if there is a feature space, whatever higher dimension it may be, why not decompose this in a hierarchical top-down manner? So a top-down hierarchical decomposition of the feature space will solve problems very fast. So then people thought of feature space partitioning, because if you want to decompose the feature space, you have to partition it. Now in what different ways? Say for example, here we have partitioned the feature space. So X is greater than equal to 10. This is imposing a partition on the feature space. Greater than 10 means this side, and less than 10 is this side. This is a partitioning of the feature space. So however, in a higher dimensional space, you need to be more specific when you talk about partitioning the feature space. So for example, here, say this is a two-dimensional space. So here when we talk about partitioning the feature space, so I have w1x1 plus w2x2 plus w0 equal to 0. If we look at this line partitions the feature space into two parts. So this is one part. In this part, say, any oblique line will actually divide a two-dimensional space into two half spaces. In one half space, you can say, if you take any point, say u2, v2, and evaluate the line, then it will be lesser than 0. On the other side of the line, in another half space, it will be greater than equal to 0, all points. So using that, you can say that whether the point lies on this half space or that half space. You can easily extend this to a plane, and that plane will again divide the entire feature space into two half spaces. And you can use a similar way by evaluating the equation of the plane and seeing that whether it is lesser than 0 or greater than 0. So that's all for feature space partitioning using oblique hyperplanes. By oblique, I mean they are not aligned with the axis. You can also use axis aligned lines. Say for example, this is again a 2D space, and if I use x1 equal to a and x2 equal to b, so if I talk about x1 lesser than a and x2 greater than b, so x1 lesser than a is this region and x2 greater than b is this region. So I will talk about this entire region by using this conjunction of these two statements. So this way I can perform feature space partitioning. So if I change this greater than and lesser than signs, I can talk about any four quadrants correspond with respect to x1 equal to a and x2 equal to b. So here you see, by using this x1 equal to a and x2 equal to b, I am imposing four partitions of the feature space. Now this way I can impose, put many such oblique lines or axis aligned lines, and I can partition the feature space in a way I like. So this is all about top-down hierarchical partitioning. Now if I think of a binary tree of depth m, where the root depth is put to 0, then in each depth, suppose there is a decision function which is of this form: hjx, j is a node index number, hjx is greater than equal to 0. And these nodes are called the split nodes because they have children, two children, and left children and right children. So if true, you go right, if false, you go left. And x is a higher dimensional data. So if you move like this, finally you may terminate at certain nodes. These nodes are known as the leaf nodes, and these correspond to the final partitions in the feature space. So if we go back to our binary search tree, then these are possibly our leaf nodes, which contain say 18, 20, 15, 17, 12 to 14, 10 to 11, and this x is greater than equal to 15. These are split nodes and the decision functions, which are deciding that how x should be routed in this yes direction and no direction, and these are also the split nodes. So coming back here, so this is a typical decision tree which performs top-down hierarchical partitioning of the split, and visually you can look at it like this. So if you look at this diagram, h1x is the first one that is to be drawn. So h1x is this one, black line. So it imposes the first partition which divides the plane space into two parts only. After h1x, you come to h2x or h3x. If you come to h2x, say, then you come to this side. So h2x again divides this side into two parts. If you come to h3x, h3x divides this side into two parts. So by using h1 and h2 and h3x, you have divided the space into four partitions. Then by answering h2x, you can go to h4 or h5. So here you see h4 is further dividing this side into these parts. So effectively, by coming to this level, h4, h5, h6, h7, you have already divided the space into 8 partitions. So this way, as you go further down the tree, up to a depth d maybe, you divide the tree, you divide the space into 2 to the power d partitions. Now, these are the nodes in the tree. So you start with the root node, which is itself a split node. Each split node puts a decision node. We are putting this notation that the root node depth is 0 and the tree depth is d, and there are 2 to the power d minus 1 split nodes and 2 to the power d leaf nodes. Now, if we look at decision trees as classifiers, as we have discussed earlier, there are hierarchical top-down partitioning. The decision functions are hosted at splitting nodes. The goal of decision tree is label, impurity, reduction, and partitions, which means that suppose you have data at one depth. Now this data is to be split in such a form so that in the next one, the data is more pure. The data is to be divided into two parts in such a way so that the data is more pure in the two divisions. Now, when we say more pure, what do we mean? So assume that there is a data set in which there is there are two classes. So one is class A, one is class B. So if there is 70% data from class A and 30% data from class B, then we will say that the dominant category is the one which has more data, which is contributing more data points in that group. So the dominant category is class A because it is contributing to 70% of data points. However, since class category A is the dominant category, so category B, which is the minority category, we will call that the impurity. Now, my job will be to increase the purity of the data set. So I will now try to divide this group, this data set, into two different data sets in such a way so that in the next one, in the left data set and right data set, their dominant category has more contribution. So that the impure data set gets divided with lesser proportion. Sorry. So this label impurity reduction in partitions is the goal of decision tree. The decision trees are learned in that way. And the leaf nodes accordingly, since in each depth we reduce the label impurity, we aim that in the leaf nodes the partitions will be more pure and the impurities will be distributed. There are two kinds of trees that we'll look at. One is having only axis aligned splits and another is having oblique splits. Now, this is one example which shows that how data flows through the tree. You can see this picture. This is a case of three categories that are there, and then one oblique partition is working and dividing the data. And as you can see here, the oblique partition is dividing the data into parts. And as it is dividing the data into parts, these diamond shaped things are basically where the pure partitions are obtained, or at least almost pure partitions are obtained. And this thing is numerically visualized here. So this is basically red, yellow, green. This way data are there. So 5,000 points of each category. It is initially divided in such a way. Then there are 4995 points of red, 3164 of yellow, and 2782 of green. Now you see only 5 points of red are here, so that they are considered negligible. Now from here, data is getting divided like this. And when it comes here, only 14 points of 14 points of green, yellow are there, and 1400 green points are there. So it is considered to be a label dominant category of green, and hence there is a green leaf. So this way, we are getting the leaf nodes. So this is how the data flow happens through the tree. I will keep this slide for some time if you want to see the data flow through the tree. And if you have any questions, please let me know.
Sir, can we apply the deep learning technique for this detection and classification?
Yes, we have tried deep learning, but there are certain characteristics of because deep learning cannot be applied for everything. The problem with deep learning in advertisement detection was this. We have also tried deep learning later for one of the papers because the reviewers raised this issue that why not try deep learning. The main issue is this, you see, because these are edited videos and there are certain constructs that are put there by the broadcasting agencies. So for example, there are a lot of windows that are put there.
Yes.
Now the classifiers fail to learn that pattern. that why these windows are there. That is one issue why we think that deep learning failed to detect the commercials.
Okay, sir.
Okay,
Yeah, yes, sir.
if you look at typically the broadcast has these windows, right? There are multiple windows they are presenting,
Yes.
and it is very random how the window styling will vary from one channel to another channel. So these are the cases where you have to use classical techniques for modeling rather than using deep learning directly. We have tried using deep learning based modeling in this case, but for advertisement detection, it failed. We have tried several techniques because the reviewers also asked us that why not deep learning, but it could not come up to that kind of classification performance. Say for example, deep learning gave us 80 plus, whereas we have reached 95, 96, even 99% with support vector machines and all.
Okay, sir.
This is a very structured image. I mean, for an example, I mean, it's a good to take very structured image. But normally, does one have to decide the threshold that beyond this, if the number is there, then we consider as impurity, like 2% or 5% or something like that?
Yeah. The impurity thing basically, say I will come to this stopping criteria and all. This impurity value, it is manually decided. Say 5% is a number, then there is another that how many data points are coming as input to the node. So that is another number. So these are the thresholds that we
Because
manually decide.
for this image, probably the things are relatively simple. But in actual practice, I understand things will be far more involved.
Yeah, it is 5% typically we keep.
Okay.
5%, 1%, but not less than 1%.
Okay. Thank you.
And also, I mean, I will show the criteria now. So this is the definition of impurity. So suppose there is the input data. So this is the data set that is input to a node. This is the data set xi, yi, I equal to 1 to whatever be the number of data points that are there. Now I have a decision function hx semicolon p. P is the set of parameters to be tuned. Now this partitions this input data set into two data sets, dl and dr. dl is the left side and dr is the right side. Now the impurity of parent, this is to be reduced when it comes to the impurity of children. Now the drop in impurity is given by delta h, and that is the impurity of the input data d and then the weighted sum of the impurities of dl and dr. This weighted sum is given by the proportion of that data that has gone to dl and the fraction of data that has gone to dr. So that is why it is cardinality of dl divided by size of input data and cardinality of dr divided by size of input data. Now see, since the impurity of d in is constant, now we have to maximize the impurity drop. So our goal is generally that minimize this quantity within this bracket. So that is taken up as a goal, that minimize this weighted sum of hdl and hdr. This is the objective function that is to be achieved, that is to be minimized for tuning these parameters. These are a few impurity measures that are there. First is known as the misclassification impurity, which is 1 minus maximum of I equal to 1 to n pi. So here pi refers to the probability of each class. So if there are say n classes in a data set, I mean I talked about only binary kind of classification problem, but there can be multi-class classification problem as well, where there can be say 10 classes, n can be 10. So it is 1 minus the maximum of all these. Then there is entropy impurity, which is mostly used. It is given by minus summation I equal to 1 to n pi log pi to the base 2. Then Gini impurity, which is 1 minus summation I equal to n pi square. You can use any one of them, especially if you want to differentiate the impurity with respect to certain set of parameters, then you can consider either Gini impurity or entropy impurity. Because misclassification impurity is not differentiable. Now, what are the termination criteria for the tree? Now, if you see that before doing any kind of tuning or deciding for impurity, for deciding for splitting, if you see that the input data to a node that satisfies any of these four properties, say for example the majority class exceeds purity threshold. So suppose I see that the majority class, its percentage is greater than 95%, then we terminate here. That means it is the dominant category. But if I see that the total number of input data that are very low, say for example if I see that only 100 points are input to the node, then there is no point in splitting it further. So there also we split, there also we stop. Now this number 100, that is decided based on the original input size. If the original input data set size is very large, then we can use the number 100. So this is basically with respect to the original input data set size. There is another thing called insufficient impurity drop. Suppose you have split because these two conditions are satisfied, the majority class purity threshold and insufficient impurity. But even then, if you see that there is no impurity drop, that means there is no point in splitting further. Maybe there is too much of overlap of different categories of data. So then also you do not, you just roll back the split. And of course, if the present node is at the maximum allowable tree depth, it must be declared as a leaf node. So then you do not consider splitting. So these are the different termination criteria for splitting the node.
Can you please go to the previous slide where there are three different ways? Okay. So why these three different impurity measures?
Oh, acha. So see, basically, when people propose decision tree algorithm, the performance of a decision tree algorithm changes with the impurity measure. You can propose your own impurity measure and show that your decision tree is performing better. There are papers that propose different impurity measures to show that with this impurity measure, the performance is better for the tree.
I see.
Okay, so it depends. Even the one that we have proposed, there are some operational differences which will come.
Okay.
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 So this is quickly, I will just show you that how to learn the axis aligned splits, for example. So suppose this is one input data set that is given to us, the top one, where there are five from the positive class and 5 from the negative class. And then there are, say, two-dimensional data given. So what we do is, we have to search for two parameters, j and theta. So in axis aligned splits, we learn rules like this, x, j greater than equal to theta. So we have two parameters to learn, j and theta. Now to do that, j is basically one of these two dimensions, dimension 1 or dimension 2, and theta is one from these values. So basically there is a brute force search. So what we do is, we first put these values, say the first dimension, in ascending order. And once we put this in ascending order, we find with respect to every point here that if we consider, say, -4, theta equal to -4 as that threshold, then that imposes a split. This is a left split and this is a right split. Then using this as j and theta, what is the impurity value? So then this side there are 3 points and this side there are 7 points. So it is basically 3 by 10. This side the impurity is 0 because all of them are negative. So it is 3 by 10 into 0. And this side it is 7 by 10 into 2 by 7 because there are 5 positives and 2 negatives. So the impurity is 2 by 7. So the net impurity is 0.2. So by choosing each of them as threshold, potential threshold, we keep on finding out that what is the impurity value. So we search along this first dimension, we search along this second dimension, and we look at every j theta combination. And we find out that for which j theta combination, we get the minimum value. And we choose that j theta combination as the proper rule for this xj less greater than equal to theta. So that way we find out this kind of a rule. So suppose this is the decision tree that we learned. So if I now have a input, say 4,7 to this tree, so see 4,7. So it is x1 greater than equal to 0. So x1, so x1 is 4. It is greater than equal to 0. So we come this way. Now it asks whether x2 is greater than equal to 6. Yes, x2 is 7. So it is greater than equal to 6. So we come this way. Now it asks x1 is greater than equal to 1. So yes, it is greater than equal to 1. So we come this way. So in leaf node, the category stored is 1. So the class level of 4,7 is 1. So this way the classification tree operates. Now one thing that you can observe here is the number of parameters that we store here is much lesser, because it is only j and theta at every node, and the number of nodes are not very high. And even if I have a very high dimensional data as input, I am only using one dimension from that to ask the question. I am not using all the dimensions. So the number of computations are also very low. So that is why the classification trees are extremely fast in operation. And even if you have very high dimensional data as input, it will still give you your output in a finite time. So the axis aligned splits typically look like this. If you look at an axis aligned split, say for example for a two-dimensional data, it actually divides the feature space like this. So this is the algorithm for axis aligned tree construction. I will just put it in this on the screen for some time. In the meantime, if you have any questions, please let me know. We don't have much time also. I think around 20 minutes. In that time, I have to finish up. If there are no questions for the participants, then shall I proceed?
Yes, sir.
Okay. So now you see we have looked at the classification tree in which we talked about the axis aligned splits. So we have xj greater than equal to theta. So in every split node, there are two parameters, j and theta. And if we have a leaf node, and if I have m classes, we basically store m parameters. It is basically a distribution of classes in that leaf node. And or we may also store just one integer saying that what is the dominant category. Now coming to the oblique split, which is basically the perceptron tree. In an oblique split, we basically store something like omega transpose x plus b greater than equal to 0. We have seen the expression for the oblique split earlier, that how it divides, it is basically not axis aligned, and how it divides it is basically a hyperplane, and how it divides the higher dimensional space into two half spaces. So here it contains capital D plus 1 parameters. And in the leaf node, it either stores only the dominant category or it stores M category information. But here we are looking at only binary classification problem. So it will store only one category. Here the termination criteria are these, that whether the majority class exceeds purity threshold, whether we have insufficient input to the node or not, or whether the nodes at the maximum allowable tree depth are reached or not. Here please note that we are not computing any impurity, but rather we are only learning a perceptron. So here I am assuming that you know how to learn a perceptron. I am not going into that. So this is a flow chart of this. So what it does is, I think I better, so suppose input to the node Q is a data set. First we see that whether the termination criteria are satisfied or not. If any of the termination criteria are satisfied, as in the axis aligned tree, then we tag the leaf node, tag node Q as a leaf node, and we put the dominant class label there. Otherwise, we perform data balancing in that node, because you see, one problem with this tree is that it is always trying to look at impurity reduction. So that is why at every node there is always an imbalance in the data. So what we do is we bring in synthetic points and perform data balancing, so that all classes have, here we are talking about binary classification problems, so that both the classes have almost equal number of points. And then we learn a perceptron, because this omega transpose x plus b, this kind of a thing is there is a perceptron. So we learn a perceptron with parameters omega q and bq from this database, from this dataset bbq, which is a balanced dataset. And then using the perceptron, we push the data to either left or right. So this is basically the flowchart for the perceptron tree construction. And here we have the data balancing algorithm. So what we do is we take the data. Suppose there are two classes from which we have the data coming in, and our main goal is that while learning the perceptron, the data from two classes, their number should be the same. So it is always there that from one class the number of data points are high, and in another class the number of data points are less. So what we do is, for both the majority and minority class, we perform k-means clustering, and then we inflate these clusters. So we find out the largest cluster from the majority category, and then first we inflate all clusters in the majority category to that size, and then we go to the minority class, and then we inflate all clusters of the minority class to a certain larger size, so that together they match the size of the majority class data. So now we have a lot of synthetic points in our data set, and we learn the perceptron from that, because perceptron is a discriminative classifier and it is susceptible to bias in data, in bias if the data set is imbalanced. So we have to always learn it from a balanced data set. Now once this is learned, then we split the training data only using the raw data. As you can see in this flowchart, we do not do it using the synthetic data, otherwise the tree will never end. So we inflate the clusters, we train the perceptron with the balanced data, and then we pass only the raw data, but not the synthetic data that we have generated there for this purpose. So this we have called the progressively balanced perceptron tree, using which we perform the classification. Now let us come to performance analysis of this proposed algorithm. So these are the names of the algorithms. PT is perceptron tree, which is a well-known tree where every node hosts a perceptron. PTDB is perceptron tree with initially balanced dataset. That means before learning the perceptron tree, the dataset is initially only balanced once. C4.5 tree is a non-decision tree where data balancing is performed with initially balanced dataset. And SVM is also used because SVM is a well-known classifier. So support vector machine is also used with RBF kernels for this. And then we have also performed perceptron tree with undersampling, because our algorithm is oversampling. So we have also tried with undersampling. Now coming to training data. So training data that we had is 25 hours of video recording from each of those 5 channels. And for testing was also 25 hours of video recording from each channel. And these are independently recorded 40 days after the training data was recorded. So at least more than a month. Now let us look at the performance analysis for different classifiers. So this is Sony 6, this is National Geographic, HBO, Cartoon Network, and Star Plus. F plus refers to F score positive class, F minus is F minus negative class, N is the total number of nodes that are formed by a tree. It is not applicable for SVM since it is not a tree type classifier. So you can clearly see that PBP tree is basically the progressively balanced perceptron tree, our algorithm. It has a lower number of nodes in all cases, and also it has the highest performance compared to others. The C4.5 tree is a well-known tree. It is almost the second performer, but it has a large number of nodes as well. So this is the performance analysis on these. Now, this is the performance analysis by varying the training dataset size. So this we have done that if we train on only 20% data, if we train on only 30% data, if we train on only 40% data, then what will be the performance on the remaining data? So it shows that what is the performance of this classifier if it is trained on only a smaller subset of data. So these are the performances that are reported here. Now, and this is reported for each of these channels. Next, the generalization capability is reported that suppose you design the system and suppose you train on only star plus, but then you test on other channels. So you design your system on star plus, but test it on Cartoon Network, HBO, National Geographic, Sony 6, and a combination of them. That is combined data, CD. Then what is the performance? So that is what is shown here, that we have trained on this and evaluated on this. So this is what is presented here, that trained on star plus on this. So you see trained on star plus, surprisingly it gives the best performance on HBO. Trained on Cartoon Network, best performance on Cartoon Network. HBO, best performance on HBO. National Geographic, best performance on National Geographic, but trained on Sony 6, best performance on HBO. Trained on combined data, best performance on combined data. So throughout, if you see, the best performance is mostly coming on HBO. So to conclude, commercial detection is a necessary first step for broadcast monitoring, and it has other applications as well. So TV broadcast video short features are used for detecting the commercials. Audiovisual short features are used for this purpose. We have explored classification trees for detecting the positives. Perceptrons at split nodes need unbiased data set. So for this purpose, we have proposed progressive data balancing for each split node. We have observed satisfactory generalization performance, and this performance can be improved further with ensemble models. So we have just shown it for trees. We can also do forests of this perceptron trees for making better generalization performance or better performance of detection. So for example, our detection performance right now is 0.92, 0.93, 0.95. We can take it close to 0.98 and so on by using random forest kind of a thing made using this kind of trees. So with this, I conclude my lecture here. And if you have, and I think I'm within time, so if you have any questions, please let me know. Thank you.
The participants, if you have any question, you can directly switch on your mic and you can ask.
Hello.
Yes.
So what I was saying, in case of wireless sensor network or IoT, where these can be applied more effectively.
Actually, these we have done for, so we have used it on televisions only. So we have taken dish TV and we have taken out data from that. And what kind of application you are looking at? Because are you looking at the application of the classifier?
No, I was thinking in the form, I'm not working into this, but I was looking at something like an intruder detection. So for example, if, in the night time, there is a camera at home and
Okay.
one tries to, because the say moment detection system give this type of follow on. If there is a cat going on there, or there is a dog or some small
Yeah.
thing.
These things can be done. These things can
Yeah,
be
so
done.
then these classifiers probably will help on the basis of the speed at which it is going, or the
No, no,
total
no.
area which it is covering, or the shape which it has. I mean, this is what I was thinking.
Right, but this classifier will not help. So for example, for these you have to go for change detection. So for this you have to go for change detection. So there are models based on Gaussian mixture model based background modeling.
Uh-huh.
That might help. And however, right now there are deep learning based models that are employed for direct foreground object detection, which can work in this nighttime and all. So that are also useful for detection of objects.
Achha. So the main idea essentially was to reduce these, false positives. I mean, something happens and it's not there actually, everything.
So actually for false positives, the present idea is that you use a classifier
Mm-hmm.
which is not heavy. Okay, which is heavy, so which is not heavy. So this is basically the cascade kind of system. So
Mm-hmm.
you use a lightweight classifier, that means which has a lower number of parameters.
Mm-hmm.
This will give you a lot of false positives,
Mm-hmm.
but it will not miss what is to be detected.
Mm-hmm.
So the total amount of image pixels will still come down. So your search region will still reduce.
Mm-hmm.
And then there will be a next set of classifiers which will be a little more heavy possibly, but will work on this set of in this set of possibly true positives plus false positives that you have detected. It will then reduce the false positives a little bit.
Okay.
So these cascade classifiers work very nicely.
Okay.
If you are interested, because actually it is not bad to have false positives, it is bad to miss.
I see. Okay, thank you.
Yeah.
Sir, any means what is the present research which is going on in this field? Means like
In which field?
in this classification of this TV space and all.
Oh,
The-
acha, so the first slide that I showed you, the very
Yeah.
first slide that I showed you, that is basically a broad overview of broadcast analytics. This is the area known as broadcast analytics. I am quickly going to that. So basically the first goal is to do broadcast segmentation. So once you perform broadcast segmentation, and then you have to take out these stories. So stories can be in multiple domains. It can be in television as video story. It can be in social media. So you can go to Facebook, Twitter, Pinterest, or you can go to web news, or you can go to radio. So there can be speech processing. So it is, you see, multimedia processing. So multiple people can collaborate and work on that. It is not only that you know speech, so you can work on speech. You can collaborate with somebody and work on image processing. So you can do these things together and you can get the stories. And it is not only stories that are there. There are also opinion articles, somebody writing an editorial about one event, or there are debates going on some event. So these debates, interviews, opinion articles, and stories, all these things should be indexed together. Now see, natural language processing comes in after this, or video analysis, or the audio text analysis, which tries to understand. So there is an understanding system afterwards, which tries to understand that what is the knowledge content of this story. So there is an opinion analysis system and all these things puts the data in the knowledge base. So this is a completely different work, that how to build up this knowledge base. And event discovery tries to link all these things. And then there is a database. This is the database construction part, which comes from broadcast segmentation, which indexes all these stories with metadata. This helps in event discovery, and this finally goes to knowledge base. This knowledge base construction is a pure AI part. Then comes this very new thing. You might have seen deep fakes. So you can have one AI anchor, this person who is completely synthetic. Say for example, this picture I have taken from China's Guha agency. They have one AI anchor. There is one news reader who is completely synthetic, and you can also interact with him. So think of interacting with a news agency where you can talk to the news agency and ask what is today's news, why this happened, why do you think this happened, or what could have happened, like this. So this kind of a conversational AI you can do. It is a chatting agent, but you are not writing, but you are talking and doing the chatting. So that is the user interaction. And along with that, you may also ask for data visualization. So you may ask that how many bomb blasts and things like that. And this guy can also show you graphs and things like that. So this is the kind of futuristic thing, the whole global goal for this kind of a system. That is the kind of research that, say, for example, 9 to 10 years that we are aiming to do.
Okay, sir.
And it is not only one person's job. It's like around 4 or 5 faculty members working together, things like that.
Okay, sir.
Okay.
Yeah, thank you, sir.
Yeah.
Okay, so any more questions?
I think Alok Gupta had raised a hand.
Alok, sir, you have any question?
No, it's fine. Sure.
Okay, sir.
I don't have any question right now.
Okay, sir. Okay, fine. Okay, sir. So I would like to thank you for this informative lecture. You have started from the history of news broadcast, then application of the machine learning for segmentation of commercial advertisement. Means it was entirely a new segment in which we means for the first time we have heard about this segment, that machine learning can be employed in this kind of commercial advertisement detection. So it was really very informative session, and decision, you have also explained about the decision tree as classifier. So this was also very informative. So our participants and me, myself personally, have gained so much from this lecture. Thank you so much, sir. Thank you.
Thank you. Thank you.
Thank you, sir.
Thank you, sir. Thank you so much.
Namaskar. So